So here's an example of how to apply Q equals MC delta T. Okay, what we're trying to do is something that we do every day when we reheat a cup of coffee. We want to know how much energy it's going to take that coffee and raise it to when it's starting off at 20.5 degrees Celsius, and we want it to go up to 95.6 degrees Celsius. And so what we're going to do is we're going to assume that coffee and water are pretty much the same thing. Coffee and water are pretty much the same thing. That happens a lot in these sorts of problems because it's just easier to deal with. Let me see if I can move my calculator so that it's a little, I don't know, so that at least it's, well, okay, you can read it. Okay, so let's call up the calculator and let's start. So if we're trying to figure out how much energy is being transferred, that's Q equals MC delta T. Okay, and so MC delta T. Do we have a mass of water? Well, no, but we have a volume. Remember that mass and volume are related by density. And so what's the density of water? 1 gram per milliliter. So basically, the mass is 250 grams. Because for water, again, 1 gram equals 1 milliliter. Okay? And then C, that's a constant. We're going to look that up. So when we look that up, the specific heat capacity for water is always 4.18 joule per gram Kelvin. And now we need to calculate the delta T. Okay, remember that's TF minus TI, and we want that in base units of Kelvin. So we have to do a little bit of a conversion here. We have to go from Celsius to Kelvin. So the way we do that is by adding 273. So 20.5 plus, so I'm trying to move the calculator so that you can, let's see, I think if I do something like this. Okay, so 20.5 plus, now it's kind of, let's get a good, okay, 20.5 plus 273, okay? And so, and I have this in scientific notation, so I'll take it out of scientific notation just because it's a little easier. Okay, so again, that's 293. So the initial temperature is 293.5 Kelvin. Okay, because that's what we started at. This is the final temperature, and so 95.6 plus 273. Okay, that's 368.6. 368.6. Okay, so both of those equal delta T. So we get delta T equals, so 368.6 plus minus 293.5. And so the difference in temperature is 75.1 Kelvin. Okay, and keep the sign with whatever the sign is. So this is a positive 75.1 degrees, or 75.1 Kelvin. So now it just becomes a plug and chug. What's the mass? 250 times 4.18 times 75.1. So 250 times 4.18 times 75.1. And so the amount of heat required to raise this, or the amount of heat that needs to be transferred, is 78,479.5 joules. Now, I will tell you that typically when we have thousands of joules, we will usually use kilojoules. So when we convert this to kilojoules, move the decimal point over 3 spots, and then we can round this to 78.5 kilojoules. And that makes a little more sense, okay, in terms of numbers that we want to be able to manipulate. Okay, now a second example here is kind of an interesting example, okay? And so we have to understand the chemical principle behind this example in order to get to the right answer, okay? It says that an 88.5 gram piece of iron has some temperature, and it's placed in a beaker containing some amount of water. And then what happens is the temperature of the metal will go down, and the temperature of the water will go up, and eventually they'll meet in the middle, and at that point there's no heat being transferred. Okay, so the point that there's no heat being transferred is a point that we call thermal equilibrium. Okay, this is not equilibrium like we just studied. That's just what it's called. When the temperature of two objects are in the same, there's no heat being transferred from one to another. But let's think about this. We have a block, and that block is going to be put into water. Okay, I wish I had blue right now, but I don't. And so what's going to happen is the heat is going to flow out of the block and into the water until they both reach the same temperature. So what we know is that the amount of heat that is gained by the water plus the amount of heat that is gained, or in this case lost, by the iron, because they have to equal each other, just one is gaining and one is losing. When you add those two things together, they equal 0. The amount of heat that's being gained by the water is equal to the amount of heat that's being lost by the iron. And so this, let's make sure we have our sign conventions down. So water is gaining heat, so this is going to be a positive value. Iron is losing heat, that's going to be a negative value. But the magnitude is going to be the same. So what's going to happen is they're going to add up to 0. So this becomes an interesting thing. We don't have the heat here. We don't have the amount of heat being transferred. But do we know what the Q of the water is? Sure. The Q of the water is mc delta T, and this is going to be the C of H2O and the mass of H2O. So all of this is all about H2O here. Okay, and now plus the Q of the iron. So now this is going to be mc delta T, and all of this is going to be of the iron here. And when we figure all that out, that is all going to equal 0. So this is kind of the interesting way that chemistry can be reflected by a mathematical equation. The energy is being transferred from the iron block to the water, and we can do this. So now, do we have the mass of the water? Sure. Okay, so I think that actually this will be a little bit easier if I go to here. Okay, here I do have blue. Let me draw this again. So we have a beaker, and inside the beaker is water, and now inside the water is that cube of iron, or a block of iron, I guess, Fe. Okay, so that's what we have set up here. Okay, so what is the mass of the water? The water was, and if we go back, we can look here. The water is 244 grams, and it's starting at 18 degrees Celsius. Okay, so let's go. So it's 200. So here's the water. Water is 244 grams, and it's starting at 18.8 degrees Celsius. Let me just double check that that's right. Okay, sure. Okay, and now the iron is 88.5 grams, and it's starting at 78.8. Okay, so let's go now. Let's figure that out. So for the iron, okay, the chemical symbol for iron is this, and so that's 88.5 grams, and it's starting at 78.8 degrees Celsius. Okay, notice what we don't have. We don't have the specific heat capacity. This is mass, and this is temperature initial. We don't have the specific heat capacity, but that's a given. And so when we do some of these problems, we may have to just look it up. Okay, so let's take a minute and look it up. So I went to the internet. I pulled up a sheet. Look, water. There's water. 4.18, and now here's iron. 0.450. Okay, so we know that this is 4.18, and this is 0.450. Okay, so what we're going to do is we want to find the temperature final, or the final temperature of the system. And I get it, you're going to be thinking, well, how are we going to be able to do that? Because the final temperature, that's going to not get us there. We have a final temperature here and a final temperature here. Aha! But the final temperature is the same for both. When we have a situation like this, the final temperature is the same for both the iron and the water. That's thermal equilibrium. Okay, so now we can do MC delta T. Okay, so MC delta T of the water plus the MC delta T of the iron, and those are going to add up to 0. Conservation of energy. The energy of the universe is constant. Okay. So now at this point, this just becomes a plug and chug. Now, it's a complicated plug and chug whenever you're solving for T final. T final is not very fun, okay? But we can still do it. So let's plug in what we get. So we get the mass here of the water. Okay, we're going to do the water first. So that's 244 grams times the specific heat, 4.18, times the change in temperature. Now, the change in temperature is TF. Remember, the TF is the same, minus the temperature initial. And let's keep in mind that the initial temperature here, we have to have it in Kelvin. So 18.8 plus 273 is equal to 291.8. Okay, that plus now the water, or the iron is 88.5 grams. Its specific heat is 0.450. Let me erase my little smiley face to give me a little more room here. Okay, times TF minus, again, temperature has to be in Kelvin, so this is going to be 78.8 plus 273, and so this is 351.4 I don't know why that's blurry. Let's see if we can get it to be not blurry. Woo! Woo! How's that? Okay. Okay, 351.8. And all of that equals 0. Okay, so now this is where the hard math comes in. And then it's not hard math, it's just, you just have to be careful with it. Okay, so you have to multiply and combine like terms and do into different like algebra stuff. Okay, so what I'm going to do is I'm going to kind of do this piecewise here. So 244, so I'm going to do this here. Okay, 244 times 4.18, that equals 1019.92. And then we haven't done anything here, so that's going to be TF minus 291.8. Okay, and all of this is plus, and now I'm going to change colors. So now we're going to do this part here, so that's 88.5 times 0.450. Okay, so this is 39.825 times TF minus 351.8. Okay, and all of that equals 0. Okay, so now we can distribute. Okay, so here we can take this and multiply it here, take that and multiply it there. So we get 1019.92 TF minus, let's say, 1019.92 times, and you can use significant figures here, but I'm going to do it all the way out, times, let's see, 291.8, and so that's going to equal 297,612. 613. I'm gonna round that up. Okay. Now I'm gonna do the same thing over here. I'm gonna distribute this and multiply, distribute that and multiply. Okay, so that's gonna be plus, okay, 39.825 times 351.8. Okay, and so that is, okay, so when I multiply that, you get 39.825 TF minus 14,010. I'll just round it there, and all of that equals 0. Okay, well, let's finish this up. One of the tricks that I was shown early on in my math career to make all of this combining easier, because we want to combine like terms, like we want to combine the TFs here. Okay, I guess that TF is hidden. Okay, and then we want to also then combine this with this. So we want to combine these two things. Those things aren't difficult to combine. It's 1019.92 plus 39.825, and so when we get those together, that's going to be 1059.745 TF. But the shortcut that I was taught once was, instead of dealing with pluses and minuses, do plus a negative, and then now that we're combining them, all we have to do is add the negative values, so it becomes a little bit easier to manage. So it's going to be negative 297,613 plus negative 14,010, and by doing that we get the negative 311,623, and that equals 0. So now we can solve for TF. Okay, so to solve for TF, we're going to take this and we're going to add it to the, we're going to subtract it, so we're subtracting a negative. So we get 1059.745 TF equals 311623. Solve for TF. So take that, and we'll go, well, I'll do 311623 divided by 1059.745. And when we do that, we get a temperature, TF, equal to 294 Kelvin. Okay, so now what's the check? The check is, when we do all this crazy math, is to make sure that that temperature falls in between the temperature of the water and the temperature of the iron, because it has to reach a thermal equilibrium. So we just made a supposition, or we just calculated that the TF is equal to 294 Kelvin. Well, what was the initial temperature of the iron? It was 352. What was the initial temperature of the water? The initial temperature of the water was 292. Now, let's think about this. The temperature of the water only changed by 2 Kelvin. But we have a lot more water than we have iron, and water has a much higher specific heat capacity. So that means that it's going to take a lot more energy to heat up water than it will to cool down the iron. So iron has to give up a whole lot of heat in order to heat water up a little bit. So this makes perfect sense chemically, and so we've just shown the math. And so that is the hardest problem that you're going to have in any one of these things. Okay, it's a problem where you're solving for the final temperature of when we're doing one of these heat transfer problems. So feel free to go back and see what it all works out to be. Just try to do it again, see if you can do the math. Just double check, because it's important that you can follow through on the math.